So what we're going to do is we're going to touch on some things about circular motion. And in circular motion, there is a type of circular motion that he has talked about, and that is gravity. And how if you have a central mass and you have a satellite mass, that in gravity, that the force of gravity on either of them from the other is the gravitational constant, mass of the center, mass of the satellite divided by r squared. So in this particular case, what we're going to do is we're going to say that a satellite with a velocity of 3,500 meters per second is orbiting a central mass at a radius of 2 million kilometers. What is the mass of the central body? Now notice specifically in this particular case I didn't give the mass of the satellite. Now in circular motion, Newton's second law reigns supreme, where the sum of the forces is equal to ma, and this particular a, because it's in circular motion, is radial. So radial acceleration is equal to v squared over r, so this is mv squared over r. So this is what the sum of the forces amounts to. Well, what's the force that we're dealing with? Well, we're dealing with the force of gravity. So the m of the satellite, because that's the mass that's moving in a circular motion, times v squared over r, is equal to that force of gravity, g mc ms over r squared. The r's cancel, the mass of the satellite cancels. So v squared r over g is equal to the mass of the central body. So the key thing for this is understanding that because it's circular motion is equal to mv squared over r, and then you have to look at the situation where hold on, I'm thinking about what I just said. That the force involved is the gravity force that comes from two bodies and their associated gravity or attraction to each other. So you get this. So this is 3,500 squared, 2 times 10 to the 6th, 6.67 times 10 to the negative 11, and that gives us a big number. But it's a central planet, so it should be big. So I get 3.67 times 10 to the 23rd kilograms. So it's an awfully big planet, but big whoop. Now, there's another type of circular motion that we'll talk about, and that is the gravitron. And if you've ever been to like the fairgrounds, they'll have this disc, and this particular disc is, let's say it is 8 meters in radius. And what happens is that the disc spins up. You're strapped to the wall on the outside, at the edge, and then they spin you up, and then what that deal is, then they go vertical. So there's a portion of you at the top of the disc where you're looking down at the earth, and then there's the bottom of the disc where you're looking up. And so the question is, granted, you're strapped in, but for the sake of the problem, what is the minimum frequency such that the people or riders will not fall off at the top? So this is definitely a circular motion problem. And so what we'll do is we'll talk about at the top of here, you have the force of gravity pulling down. At the bottom, you also have the force of gravity pulling down. Now, one of the things that you feel, and this is kind of what, I hate saying the word because some people get so, some professors get so irrational when they hear it. You think about centrifugal force. Like when you turn your car, you feel that pull outward. And what it really is that when you turn the car to the left, Newton's first law says object in motion stays in motion. So really, your thing that you're feeling pulling you to the outside is really your body wanting to continue to move in a straight line, and the car door is pushing you inward. So you feel that door pushing inward, so you interpret that as a desire of you getting pulled outward. At the top, so what we call this, it's the normal force. It's the force of the wheel pushing on you. And for there, it's upward as well, it's inward as well. Now, in circular motion, the radial acceleration is always pushing inward. So here it's pushing inward as well, and there it's pushing inward as well. And what we're going to do is we're going to say that up is positive and down is negative. So at the top, the normal force is going to equal 0. The normal force is the force of the wheel on you. Now, when it's exactly 0, when the normal force is 0, you would have that brief moment where you feel like you're in free fall. So that, if it goes any slower, you're being pulled off the padding. Any faster, then the normal force will start increasing and push, and you'd feel that push downward. So it's circular motion, so the sum of the forces radially is equal to MAR, which is equal to MV squared over R. AR is down, so it's negative. And that is equal to the force of gravity, which is minus mg. So the negatives cancel, and the m's cancel, and so you're left with v squared over r is equal to g. So v squared is equal to gr, or v is the square root of gr. And so that is the minimal linear velocity at the top, or the minimum linear velocity of the object such that you stay on. So how do you get the frequency? Well, we use, in circular motion, there are some conversions. V is equal to omega r. and 2 pi f is equal to omega. So this v that is equal to the square root of gr is equal to 2 pi f r. The 2 pi f gets substituted for omega, and then the v gets substituted with the square root of gr, and then the r comes down. The goal is to get the frequency. So what I'm going to do is I'm going to divide both sides by 2 pi r, and that is equal to f. Now, just to do some things, just to simplify it, this is 1 over 2 pi square root of gr over r squared is equal to f. I brought the r underneath the radical, and when you do, you've got to square it. So it ends up as 1 over 2 pi square root gr over r squared. One of them cancels, and the frequency is 1 over 2 pi g over r. Oh, I said the radius was 8. Did I do that? Yeah, I said it was 8. Should have said it was 9.8 just to make it. So the frequency is 0.176 hertz. And we could also say that the period, to give us a better indication of the motion, is the inverse of frequency. And the inverse of 0.176 is 5.68. So what I had initially is something akin to square root of r over r. Now this becomes square root of r over square root of r squared. The r is effectively the square root of r squared. And so that becomes r over r squared, or the square root of 1 over r. So if I just did what's the square root of r squared, you would go, oh, that's just r. Yeah. So you could go the other way. You could say r is equal to the square root of r squared. Okay. The other thing that I would just like to show is what is the normal force at the bottom. So at the bottom, the radial acceleration is up, the normal force is up, and we still have the force of gravity pulling down. The sum of the forces radially is equal to mv squared over r. Now A is up, so this is positive. Now the normal force is up, Fn. The gravity force is down, minus Fg. So the normal force, now this is at that minimal velocity where the normal force at the top is 0. So now we're going to find out, well, what's the normal force at the bottom? The normal force is mv squared over r plus Fg, or mv squared over r plus mg. And what I'm going to do is I'm going to pull out the m. The V in this case we never actually found the V. Hold on. We just substituted it out. So V is the square root of GR. Oh, this is great. So this is M square root of GR squared over R plus G. Because V is the square root of GR that we got over there. So that becomes M GR over R plus G, or 2mg. So the normal force is twice that of the force of gravity. So at the top of the curve, you're feeling nothing. At the bottom of so you feel like you weigh nothing. At the bottom of the curve, you feel like you weigh twice as much as you normally do. And so that shows that at the top you feel lighter, at the bottom you feel heavier. So if we have more time with circular motion, I could do the water slide loop-to-loop problem, but that's for another day. All right, now after circular motion, one of the things that they add is energy. Oh, and we are going to do inclined planes because I'm going to show you how awesome it is. Yeah, we'll do inclined planes as well. Now, with energy, there is kinetic and potential.
I watched your video.
I was like, this sounds familiar.
Yeah, this one was like extremely
Okay. With kinetic, and I don't write, my nomenclature is a little bit different, but kinetic energy, that's my symbol. It's 1/2 mv squared. Now potential divides into two. There's gravitational and then there is spring. Gravitational potential energy is mgh. Spring potential energy is 1/2 kx squared. Now the spring potential energy, there is a derivation, but we would have to use calculus, Hooke's law. And Hooke's law is saying that the force, negative kx, where x is the displacement, F is the force, and K is the spring constant, which has the units of newtons per meter. I have tried to write right-handed, and it's horrible. Why would you oppress me with that? Let's explore this. Why did you suggest, do you think I would write better right-handed?
No.
Why did you ask the question? I'm curious now.
I'm struggling to see you.
Oh, that's right, because of my big fat left hand. I understand. It's one of the reasons why, and this is one of the reasons why I do the half sheets.
Yeah.
And so it's just a natural thing. On whiteboards, what's interesting is that everybody comes into the room thinking that the professor is right-handed, so they sit on the left side. I walk in and I do it, and my back blocks the whole thing, so the next lecture, everybody swings around to the other side.
It kind of does help, though, to make you actually stop and listen. I can't see what you're writing.
Yeah, it eventually you develop an awareness of, this is one of the reasons why I frequently pull my hand out, I do the switches, but there's sometimes it's like, dude, I gotta write this down.
Yeah.
And if anybody wants to donate like at least $1,000 to me, or give me 1,000 or 2,000, there are those electric tablets that are big, like bigger than an iPad Pro, and you use special pins, and it feeds directly into the monitor, so you don't even see my hand.
They don't work.
They don't, yeah, and so.
My math teacher used it.
Yeah.
It was even worse.
That
Even
kind of
like,
makes sense.
you spend the whole year trying to learn how to use it, and then really start telling them.
Yeah. So yeah, even if you did, you'd still be looking. I mean, and
It's fine. I'll just.
is this not a nice hand? I mean, this is a very nice hand.
Yeah.
And one of the things that's a bit of my uncle is left-handed. He does everything left-handed except right left-handed. And why is that? Because the nuns beat his hand, and if he picks up a pen with his left hand, he has these violent flashbacks.
Yeah.
And so that's why, like, get a little bit antsy when people.
PTSD.
Yeah. Thank you for bringing that up.
That's funny though. My dad was left-handed and he broke his left arm in third grade and learned to write right hand.
Yeah.
He liked his left hand his third grade.
It's interesting.
Crazy, yeah.
That's interesting. All right. So for something like this, what we're going to do is at the top of the hill, there is a spring where K is equal to 500 newtons per meter, that the compression distance is 2 meters, the mass of the object is 5 kilograms. The hill height is 30 meters. What I want to know is, so there is position A, and position A is compressed. Top of hill. There is B, which is uncompressed top of hill. A is also not moving. B is moving. C, so A is there, B is there, C is uncompressed, bottom of hill, moving. And then, I mean, I wouldn't expect this as one problem. This is actually like 3 problems. It enters a region where the coefficient of kinetic friction is 0.2. And so D is where it stops. And so that is, I need a variable. D, little d. So the first question that I have is, what is the potential energy at A? The compressed top of the hill, that works better. It's compressed and at the top of the hill. So that is potential energy due to gravity and the potential energy due to the spring. Well, that is mgh, and the potential energy at the spring, or due to the spring, is 1/2 kx squared. So this is 5 times 9.8 times 30. K is 500. X is 2. Yeah, we're at a good stopping point. So I get 2470 joules. Correct. Because the compression distance is 2.
I'm getting 1,147.
As her?
Million.
Okay. Oh, okay. Now.
Oh, I was doing times 3, not 30.
Yeah. I encourage multiple people to check the numbers. Can't trust old people. You can get it wrong. But sometimes I get it
I
right
got what you got.
with my dumb left hand.
Yeah, you say people who are left-handed are smarter.
Yeah.
What's really weird, I mean, if we're really going to explore my psyche, my precision motions, anything that requires precision, I pick up left-handed.
Yeah.
Anything that requires power, I do right-handed. So I throw right-handed. As a kid, I was tortured because I caught right-handed and threw right-handed. So I would catch the ball with my glove, take the glove off, and then throw it. So I never made any baseball teams. Thank you for bringing this up. So
So bad for you.
I had a horrible existence. No, I was fine because I eventually figured out I really knew math, and no one else did. So.
No, I played college baseball with a buddy who was kind of like that.
Mhm.
He had a girl that could switch.
Yeah.
And like he would catch it right-handed and throw the glove and like pop the ball, catch the ball and throw it back. What the heck? What are you doing?
All right. So one of the things that I want to know is, so this potential energy at A is actually the energy at A because there is no kinetic energy. So the question that I have is, what's the energy at B and what's the energy at C? And since there is no friction from A to C, for both of those cases, it's also 2470. You don't have to recompute because energy is conserved. No friction, yay, no friction.
So if it doesn't have friction, you don't use kinetic energy?
You don't need to use kinetic energy. It's unnecessary to. I mean, eventually we're going to get into it. But what I'm doing is I'm showing you the idea of conservation of energy. That if there now, granted, the energy at D is not 2470 because you got friction. Friction is bleeding the energy away.
Yeah.
So we calculated the potential energy, but that's because there's no kinetic energy.
Correct.
Total
Mhm.
energy, but at B it's kinetic and potential, but they just add
Correct.
up to that.
But it would add up to be 2470 anyway.
Yeah.
So what we can do is, what's the velocity at B, the uncompressed situation? Well, for this, the energy at A is equal to the energy at B. There's no friction during the uncompressing of the spring. The energy at A is potential energy of gravitational plus the potential energy of the spring. The energy at B is the kinetic energy at B plus the potential energy due to gravity. And I'm using the same notation. Both of those are mgh, and h in both cases is equal to 30. So those things are equal to each other. If the surface remains level, you don't need to put that in. It's kind of like the appendix of the problem. You can just cross them out. And that means that the potential energy of the spring, 1/2 kx squared, is equal to 1/2 mv squared. So k over m x squared is equal to v squared. So v is x times the square root of k over m.
So you're basically saying since A and B are at the same height, there's no reason to use.
There's no reason, yeah. Moving across a surface here, or moving across a surface in Denver, or moving across a surface in the Dead Sea, all it cares about is the change in height to each other, not where it is in the universe.
So since they're the same height, you don't have to.
You don't have to use the potential energy.
Yeah.
So the velocity is 500. Ooh, I like this number. Divided by m, which is 5. That's 100. Square root of 100 is 10. So the velocity is 20 meters per second. Exact.
Why is it not kx squared over m?
It is, but I kept the x to the side.
Okay.
I mean, this is equivalent to kx squared over m.
Okay.
It's just that's just aesthetics.
Okay.
Because what I was doing with this is I was lining up the fact that square root of x squared is x, and square root of k over m is that.
Okay.
So it's kind of a... Sometimes physics is more of an art than actual physics. Not many people get that, so... So you're saying I'm destroying your knowledge of physics? Is that what you're doing?
I don't know why it's throwing me off. I understand the height thing, but that's,
Okay. Now, what we're going to do is I'm going to compute what is the velocity at c. And what we can do is that because there is no friction during this motion, I could either use the energy at A is equal to the energy at c, or the energy at B is equal to the energy at c. Either one would work. We don't really have the time to explore all the permutations, so we'll do energy at B is equal to energy at C. Energy at B is the kinetic energy at B plus the potential energy at B due to gravity is equal to the kinetic energy at C, the bottom of the hill. Since it's at the bottom of the hill, what I typically do is I say that that level has an h of 0. So I'm not really concerned about the height at C because it's at 0, so
you made it 0.
I made it 0, yes. And the m's cancel, so it's unnecessary for the mass. There are certain situations where, given the problem and the mass isn't given, if it's not given, either A, he made a mistake, or B, it was intentional. What would cancel? No, the B's are subscripts.
No, the B.
Why would the V's cancel? They would have to be in all three terms.
Oh, yeah.
Yeah. It's a common mistake. So now multiply everything by 2. Square root it. Now the VB won't go to VB, or VB squared won't go to VB, but it will do that. And that is, let me use the right
And we didn't use potential energy, like, we didn't make it equal to kinetic energy at C plus potential energy at C because it's
Well, we didn't use the potential energy at C because there is no potential energy. But the height at that particular point is 0.
Yeah.
So that's why I didn't include it. I mean, I could, but I'd plug in an h of 0 and then it would go away. Yeah. So for the last part, what I want to know is, what's the distance d? What's the distance d that it traveled when it comes to a stop? And for that, what we'll do is, here is point C, and there is point D. And there is a region of length d where there is a coefficient of kinetic friction of, what did I say? 0.2. So we have that. The reason why I'm using C with D is because it's a level surface. I'm not going to include any mention of potential energy, because it's 0. So what I'm going to do is, I'm going to say that, I'm going to write this, that the energy at C minus the work, the energy removed through friction, is equal to the energy at D. Now the energy at C is 1/2 mvc squared minus the work is equal to, it's on a level surface and it's not moving, so that's 0. So 1/2 mvc squared is equal to work. Now, how do we get the work? Well, work is force times distance. The force is the frictional force. The distance is the distance d that we need. Well, how do we get friction force? Well, this object is on a flat surface, Fg down and Fn up, with friction force going to the left because the velocity is going to the right. When you do these force diagrams, remember, one of the things that you do is you learn the little ticky-tack things that just make the professor freak out. And one of them is, make sure that the forces on your force diagram meet at a point at the center of mass of your object. Don't have them touch different parts. They all have to come together to the same point. This is a reason why I have velocity out to the side, which was because the velocity isn't a force. I'm just using it as a reference. So it's technically not part of the force diagram. Well, the sum of the forces in y is equal to 0, which is equal to normal force minus Fg. So the normal force is equal to Fg. So the normal force is equal to mg. Well, the friction force is mu sub k times normal force, which is the definition. So this is mu sub k mg. Which means that the work, which is the friction force times the distance, is mu sub k mg d. That makes this 1/2 mvc squared is equal to mu sub k mg d. Work is change of x over change in t? No. Change of x over change in t is velocity. So VC 31.4 squared. 2, 9.8. Oh, bummer. I know. I just heard. I know. She spoke up sooner. 9.8 times 0.2. I get 251.5 meters. So that's how far it slid. Thank you. That's how far it slid before it came to a stop. Okay. Now what we're going to do now is we're going to do an inclined plane with friction. And do you think you would do it with energy or with motion? Energy? Okay, we'll do it with energy. Yeah. All right, so what I'm going to do is we have a slope, we have a mass is 5 kilograms. We have a coefficient of kinetic friction, which is 0.1. This length here is distance L, which is 70 meters. The angle theta I'm going to set at 60 degrees. Now it has just overcome friction. If it starts from rest, what is its velocity at the bottom of the hill? And really, if it gets to the point where he goes, you got an inclined plane, and he says you're allowed to use either motion or energy. Don't care which. If he says something like, give me the time it takes for it to get to the bottom, the fastest way is to use motion. If he says, give me the velocity at the bottom of the hill, and that's the only thing I care about, you go straight to energy. The energy equations are way more efficient than motion to calculate the final velocity. It's a very simple thing. No, not so simple. So for this, what we'll do is that is point A, and that is point B.
Could we do motion also after?
Yeah, we'll do motion after. And what we'll do is we'll do motion after to get V, and you'll get the same answer. So we'll do it both ways. Now, there is friction, boo friction. So what we do is what we call my checking account equation. That the energy at A minus the energy removed through friction is your final energy, or as I like to say, the money that you start out with minus the money that you spent is equal to the money that you have at the end of the day. Well, what is that A? Well, it is entirely the potential energy at A. Why is there no kinetic energy? It's not moving. Well, the work, the energy removed through friction is still there. The energy at B is the kinetic energy at B, and that is there. So what I'm going to do right now is I'm going to do a force diagram table for this guy. We're going to use it for this, and we're going to use it for the motion equation. So we're just going to knock it out in one shot. Now this is the inclined plane and that is the object. Now, the force of gravity is still like that. But I know that the normal force is like this, and because velocity is going down the hill, the friction force is like that. What I'm going to do is I'm going to break apart the force of gravity into its components. And what I'm effectively doing is I'm rotating the frame of reference, so now that everything is either vertically or horizontally along with the plane of the slope. So this force of gravity makes it look like this. And that is also the angle theta, which is 60 degrees. Now, FGX is, well, hold on, back it up. Cosine of theta is adjacent over hypotenuse. So this is FGY over FG. So FGY is equal to FG cosine theta. Sine theta, which is opposite over hypotenuse, is FGX over FG. So FGX is FG sine theta. Now, why did I go through all this business? Because we first have to get the normal force. The normal force is very useful, and we're going to use it for both situations. That the sum of the forces vertically is equal to 0. And when we mean vertically, we mean the rotated y. And how do we know that it's 0? It's not flying off, it's not penetrating the surface. We're good to go. So now, this is Fn minus Fgy. So Fgy is equal to normal force, and Fgy is Fg cos theta. Now, the friction force is the normal force times mu sub k. Get that in now. So the friction force is mu sub k mg cosine theta. Now, when we do the inclined plane with motion, this is all we need. But what we really need for the problem that we have here, we need what work is, which is the friction force times distance. So this is mu sub k mg d cosine theta. So this equation here becomes mgh minus mu sub k mg d cosine theta is equal to 1/2 mv squared.
Which equation is that?
It's that one. That one goes there. And one of the things that we have an issue with is I don't know what h is. So what we have to do is we have to substitute it out. And what is h? H is that height right there, the height at A. Well, if I don't know h, I have this angle and I have the hypotenuse. So sine of theta, which is opposite over hypotenuse, is, now this h is the length h. The hypotenuse is L. So h is L sine theta. So this equation here, the m's cancel. And I'm left with GL sine theta minus mu sub k GD cosine theta equals v squared over 2. I'm going to factor out a g. Multiply by 2. Oh. Clarification, what is d? That's the distance down the hill. So what is another way of expressing d in variables here? It's the distance from there to there. It's L, correct. So what I'm going to do is keep that d. That d becomes an L cosine theta v squared over 2. Factor out an L.
Wait, so if we multiply the two over, isn't it just v squared?
Yes. Thank you. And so the final velocity is that. So what we do is 2 times 9.8 times 70 sine 60 minus 0.1 cosine of 60 and I get 33.46 meters per second. And that's the velocity at the bottom of the hill.
I got a question.
Yes.
How'd you go from force of friction equals proportional force in K, that bottom part?
This thing?
Yeah, like why'd you throw the bottom? The force equals.
Well, the thing is that I know what the potential energy at A is, and I know what the kinetic energy at B is, but I don't know what work is.
Yeah.
How do I get work? Well, I got to first find the normal force, then I find the friction force, and then I know work is force times distance to get that. Okay. Now what we're going to do is we're going to do the same problem. But instead of using equations of energy, we're going to use equations of motion. Now, the first step for using equations of motion is find the normal force. And we did that here. We found that the normal force is mg cosine theta. And we figured out that it's mg cosine theta because we used this force diagram. We then figured out that the friction force, which is force or normal force times distance, or in this case, since the distance is, back up, not that at all. The friction force is mu sub k times normal force, so this is mu sub k mg cosine theta. So the friction force is that. We did it 2 pages ago, but we're not going to work with work. We're going to work with a different equation. We're going to work with the sum of the forces in X is equal to MAX. And when you look at the force diagram, there are only 2 forces acting in X. The friction force and FGX. And FGX is FG sine theta. Now in this particular case, FGX is positive and friction force is negative. So it's minus friction force plus FGX. AX is minus F sub F plus FGX over M. Now the friction force is minus mu sub K mg cos theta, and FGX is positive mg sine theta, and we divide by M. I could factor out an M, but the end result would be that everything cancels, or that the M's cancel. And I'm left with G sine theta minus mu sub K G cosine theta, or G sine theta minus mu sub K cosine theta. Now that's the acceleration. Now that we have acceleration, it effectively becomes a one-dimensional motion problem because this object is accelerating at a distance L. So it's a one-dimensional motion problem. Well, what do we do with one-dimensional motion problems? X equals x naught plus v naught t plus 1/2 at squared, and v equals v naught plus at. Like any good one-dimensional motion problem, you set the origin to be at the top, and we also note that the initial velocity is 0. It starts from rest. So that's 0, that's 0, that is 0. We identify what we know and don't know. I know X and A. I know A, but I don't know T. So to get V, what I'm going to do here is I'm going to solve for T and then plug it into here. So 2x over A is equal to T squared. Or T is the square root of 2x over A. I'm going to plug that T into here. V equals A times T, which is 2x over A. Now I'm going to bring the A inside. So that makes 2xa squared over a. 2xa. And a, well, the thing that I want to say is that x is the length L down the hill, and a is this, so I'm looking at 2lg sine theta minus mu sub k cosine theta. And that is the equation for the final velocity. Now, we could plug it in and prove it, but let's take a look at this using the equations of energy. We got the same equation. It should be the same. It's physics. So we plug it in and we get the same number, 33.46. It doesn't really matter. But what you see here is that with motion, there are quite a few extra steps. But with energy, it's a fairly straightforward situation.
And motion is the F1 material.
And if I was going to ask, now we could do all sorts of things like how long did it take to get down the hill, which is now you're going to be using variants of these. But if he said how long it went down the hill, I would use motion. If he said what's the velocity at the bottom of the hill, I use energy. Yeah, I have two problem sets that shortly before test 1, I have them do these 9 motion problems. Then we take test 1, and a couple weeks later, right before test 2, I give them the same 9 problems, and I say, only use energy. And then compare the velocities that you get using energy with the velocities that you get using motion. Are they equal? And they go, yeah. And they're just amazed. And I'm like, I know, it's physics. It's the same thing. So. All right. Okay. Now, we're going to move on to collisions. Elastic collisions are on the table, so we can do elastic collisions. My recommendation is that elastic collisions there's some rough stuff. But what we're going to do is we're going to look at a particular multiple choice where in elastic, they're rare. Momentum is conserved and energy is conserved. In inelastic, they are quite common. Momentum is also conserved, but energy is never conserved. And this energy that we're talking about is mechanical energy, the energy of motion and stuff. Technically the energy is still there, but it's transferred into crushing of material, the physical shape changes, the heat, sound, stuff like that. Now, a very simple problem that we could do for inelastic collision is the lab experiment that we did. You have a bullet. The mass of the bullet is 0.01 kilograms, and it's moving at a velocity, or an unknown velocity, and we're going to be looking for that velocity. It hits this arm and ball mass, and that mass is 0.2 kilograms, and that initial velocity of the arm is 0. once it embeds itself into the ball, you see the word embed. That means sticks, and that means inelastic. If you see embed or stick, that's an inelastic collision. So for this, the angle here is 60 degrees, and the length is, we'll make it interesting, is 5 meters. So the question is, what is the velocity of the bullet when it impacts the bigger ball? It's a two-part problem. The first part that we do is actually conserving energy. And it is after impact to top of curve, or to the top of the arc, or whatever, when it comes to a stop right here. So after the impact, the velocity is merely 1/2 mv squared. And this particular m that I'm writing is the combined mass of ma and mb. At the top of the curve, it is purely potential energy. So it is mgh. The masses are the same, and one of the reasons why I never made a big deal about writing it out completely like this is because the masses cancel out. So v squared is equal to 2gh, or v is the square root of 2gh. And now we're going to have to do just a little bit of geometry to explain what h is. That right there is h. That length there, which is L, is the same as that length there, which is L. That's the string, that's the arm. It does not change length, even though it's at a different angle. That's my angle theta, which is 60 degrees. So if this is length h, that is length h, and if that is length L with that as h, that length is L minus h.
So this is an inelastic
Correct.
collision.
And why is it inelastic? Because that thing sticks.
So why are we conserving energy?
Because what we're doing, excellent question. I'm so glad you asked. Look at these 2 points that I'm comparing. I'm comparing from after impact, the moment after they completely stick together, to the top of the curve. So from there to there. There is no collision in that particular case.
Okay.
So that's why I'm allowed to conserve energy. We're going to get to the inelastic part in just a moment. Now for this, cosine of theta is adjacent over hypotenuse. I'm going to write that out so that I don't get confused. The adjacent side is L minus h. The hypotenuse side is L. So we're working with that side, and that angle. That means that L cosine theta is L minus h. Now I'm looking for h. So I get this. So this V is the square root of 2GL 1 minus cosine of theta. Now, so this is the velocity necessary to cause this system to go up a particular angle theta. Now we're going to get to the collision part. So pre-collision and post-collision, there was a collision in the middle where they stuck, so this is inelastic, so we conserve momentum only. In this particular case, yes, we conserve momentum. That initial momentum is the mass of the bullet, velocity of the bullet. The arm is not moving. Post-collision, the momentum is mass of the bullet plus mass of the arm times its velocity post-collision. The velocity post-collision is that expression right here. So what I'm going to do on the next line is MB/VB is equal to MB plus MA times the square root of 2GL 1 minus cosine theta. The whole goal is to find VB. So VB is MB plus MA over MB square root 2GL 1 minus cosine theta. So the mass of the bullet, 0.01. Mass of the arm, 0.2. 0.01. 2 times 9.8 times 5. 1 minus cosine of 60. And I get an answer. That bullet's moving pretty fast. 1,029 meters per second. But big deal, it's a number. I mean, I just did this dynamically. If I had time, I would change the numbers so that it wouldn't be as big. Yeah, that's a bullet going about Mach 3. It's fine. That's an engineering problem. That's not my problem. I'm a physicist. I just write stuff. So that is an inelastic collision. And so what we're going to do is we're going to do one of those wretched elastic collision problems. And hopefully we will never face one. Now, what I'm going to do is, I saw this elastic collision problem going on, and what it was is the dude had set up some carts with magnets, and the cart on the left was heading to the right at 5 meters per second, and so that is V1. The cart on the left was heading, or the car on the right was heading to the left with a velocity of negative 2.5 meters per second. To make this easier, and he did this in a multiple choice, but I'm going to alter it just a little bit, is that the mass of cart 1, oh no, I'm not going to do that. Let's make it, mass of cart 1 is 1/10 the mass of cart 2. And the question that I want to know is, or the answer that I want to know is, what is the new velocities of cart 1 and cart 2? Now, how they bounce off elastically is that they have magnets at the front of the car, and each magnet has the North Pole at it. So they'll never come into physical contact. The magnetic fields will interact with each other and cause them to bounce off. And so this is an example of an elastic collision. Billiard balls are technically inelastic, but they're real close to being elastic. So how do we do this problem? Well, it's elastic, so the initial momentum is equal to the final momentum, and the initial energy is equal to the final energy. Those are true. This elastic collision problems at their core are 2 equation, 2 unknowns. The initial momentum is m1v1 plus m2v2 is equal to m1v1 prime plus m2v2 prime. And the energy is 1/2 m1v1 squared plus 1/2 m2v2 squared is equal to 1/2 m1v1 prime squared plus 1/2 m2v2 prime squared. Now what I'm going to do first is get rid of those halves. The next thing that I'm going to do is I'm going to substitute in that m1 is 1/10 m2. So this is 1/10 m2 v1 plus m2 v2 is equal to 1/10 m2 v1 prime plus m2 v2 prime. And as you can see, there's an m2 in every term, so those m2's cancel. You don't need to know the specific mass of m1 or m2, you just need to know the ratio of their masses. You do the same thing here. m2 over 10 v1 squared plus m2 v2 squared equals m2 over 10 v1 prime squared plus m2 v2 prime squared. And again, the m2's go away. Now what I'm going to do is I'm going to write 1/10 v1 plus v2 is equal to v1 prime over 10 plus v2 prime. And then I'm going to have from the other one v1 squared over 10, and that one goes away. v2 squared is equal to v1 prime squared over 10 plus v2 prime squared. So it simplifies a little bit. Now what I'm going to do is, in a moment of rare honesty, occasionally Dr. Eschenberg plugs and chugs as well. And it's in situations where, honestly, it just makes things go so much more smoothly. And what I do is I plug in my V1s and V2s. So this is 1/10 5 minus 2.5 is equal to V1 prime 10 plus V2 prime. So we end up with 2.5 divided by 10, or 0.25, is equal to V1 prime over 10 plus V2 prime. I do the same thing here. 5 squared over 10 plus negative 2.5 squared is equal to V1 prime squared over 10 plus V2 prime squared. 25 over 10 is 2.5 plus 2.5 squared, and I get 8.75 equals V1 prime squared over 10 plus V2 prime squared. If I simply gave you those two equations and I said solve for V1 prime and V2 prime, you'd look at it and go, that's not that bad. The whole thing about an elastic collision problem is setting those two equations up and getting it to that point. Once you get it to that point, it's all downhill from there.
I had a question about the last one.
When we get back to that.
Yeah.
So what I do is I follow the procedure. I'm going to move that over and solve for V2 prime. So V2 prime is 0.25 minus V1 prime over 10. I'm going to take that V2 prime and plug it in here. So this makes it 8.75 equals V1 prime squared over 10 plus 0.25 minus V1 prime over 10 quantity squared. 8.75. Are you writing this down, or are you?
I was looking at it.
Oh, okay. All right.
For like the math all the way over there, where it's like the 1 times V1 plus V2, why is your 5 minus the 2.5 in parentheses? Shouldn't like the 5 go to the 10 first and then the negative? Like at the very end. But
This is the expression for V2 prime.
no, like where it says 1/10 V1 plus
The other
V2.
side.
This one?
Yeah. Shouldn't that just the 5 go over the 10 first and then the 5 and the 2.5 do the parentheses and then 1?
All I did was move that over here.
No, like the very top. When you
Oh,
say-
this one?
Yeah.
All I did is the V1 is 5 and V2 is negative 2.5.
But shouldn't the 5 times the 1/10 first and then the 10? Because that would be negative 3 or something.
Dang it. All right.
You get what
Thank
I'm
you.
saying?
Yeah, I know exactly what you're saying now. So, and this is the error of plugging and chugging. So, it's not that, it's that. So it's 0.5. This is 1/2 minus 2.5. So it's not 0.25, it's minus 2. Which makes that minus 2. Which makes that minus 2. All right, we're back on track. You put in a parentheses and the whole thing blows up. Now, V1 prime squared over 10 plus 4 plus V1 prime squared over 100. In the middle, it's positive 2V1 prime over 10, or positive 1/5 V1 prime, so it becomes positive 2/5 V1 prime. So I really don't need the parentheses. Now, we're going to do this the right way. V1 prime squared over 10, so 1/10 plus 1/100th is 0.11 V1 prime squared plus 2/5 V1 prime. Bring that over and it's minus 4.75. The 0.11 is the A. The 0.4 is the B. And the minus 4.75 is the C. And those are our prefixes for quadratic equation. And since I have an app for that, I'm going to plug that in.
Did you FOIL that one yet? Is that how you got the 2/5 V1 prime?
Yeah. So the two expressions for V1 prime is either negative 8.64 or 5. So what I'm going to do is I'm going to get both sets of numbers. If V1 prime is equal to 5, then V2 prime is equal to negative 2 minus 5 over 10. So V2 prime is equal to minus 2.5 meters per second. Now, this is a nonsensical answer, and I will tell you why. Object 1 was on the left. Object 2 was on the right. So what happens is they're coming at each other, and then afterwards, 1 is continuing to go to the right, while 2 is going to the left. That implies that they passed through each other. That is not physically possible. So it is not that solution. So it has to be V1 prime is negative 8.64 meters per second. So V2 prime is equal to negative 2 minus a minus 8.64 over 10. And I get negative 1.136 meters per second. So the object on the left will rebound and move to the left at 8.6 meters per second. The object on the right will continue to move to the left but at a slower velocity. So they do not pass through each other. And so that reality is maintained. So those are my velocities. The elastic collision, in my estimation, is a time sink. Like, you could give it as a problem. It's a legitimate problem. But what you would have to do is I would basically double the points for the problem. But I think it's the technique that I think is very interesting just to look at, to see the algebra work out in a way. And I normally assign a problem like this to make them appreciate the fact that we're not doing it on the test.
Can you mind if I ask you my question?
Mhm.
Okay, it was about the inelastic one. I just wanted to know when we were solving for h, why we use cosine.
Because in this situation, cosine of theta is the adjacent over the hypotenuse.
Yeah.
That is theta. The adjacent side is L minus H. The hypotenuse side is L.
Yeah.
So when you bring up the L, you get this.
No, yeah, like I was like, why did we use cosine theta? Why didn't we use sine theta?
Because sine theta would be the side that's here,
Which we don't know.
which we don't know. We know nothing about. But I do know what L minus H is.
Gotcha. So that you just picked whichever one you could.
Yeah, whichever one I could determine.
Okay. Gotcha. I just didn't know if there was like a reason other than that.
Other than the fact that I knew everything about it.
Yeah.
And I didn't know what sine is. Yeah.
Exactly.
Okay. Conservation of angular momentum. So for something like this, an example that I have is you've got two disks. The mass of disk 1 is 20 kilograms. It has, think of this as a big record player, huge record player. The initial omega is 0, so it's not rotating at all. And that record, and I use that word loosely, is going to fall on top of and stick to a disk. The mass of that disk is 40 kilograms, and its frequency is 0.5 hertz. What is the final frequency? So the top disk, which is at rest, falls on the lower disk and sticks. The initial frequency of the lower disk is 0.5 hertz. What is the final frequency? So that's what we want. Because they stick and they are rotating, we use conservation of angular momentum, which means that the initial angular momentum is the final angular momentum. Well, L is I omega. So L is I initial omega initial. L final is I final omega final. Now I initial is the moment of inertia of just that disk. Now these are identical radius disks, but different masses. The initial moment of inertia, since that is, that's not moving, but that one is 1/2 m2 r squared. Let's make the r 3 meters. Two pi f is equal to omega. So initial omega is, and actually I'm going to change the stuff. That's the initial frequency. So the initial frequency is 2 pi initial frequency. The final moment of inertia is the moment of inertia of disk 2 plus the moment of inertia of disk 1. And omega final is 2 pi frequency final, so this is 2 pi frequency final. So the 2 pi's cancel. Now, there are some other things that we could simplify, but what I'm going to do is clean it up. 1/2 m2 r squared fi is equal to, that 1/2 factors out. Oh, and the r squared factors out as well. And I'm left with m2 plus m1 frequency final. Now, one of the interesting things is I did not have to give the radius of the disk because the r squares cancel, as well as the halves, but big deal. And I'm left with m2 fi is equal to m2 plus m1 final frequency. So m2 fi over m2 plus m1 is equal to the final frequency. And that means it is 40, 0.5 over 40 plus 20, or 0.34 hertz. And so that is a conservation of angular momentum problem. You can do the same thing with the ice skating problem. You can do all sorts of things. But for the disk, the core equation is knowing that angular momentum is conserved and that angular momentum is I omega. All right, let's move on to torque bars, and I think that will be enough for tonight. So for a torque bar, what I'm going to do is I have a 20 kilogram mass. X1 is 4 meters, and X2 is 3 meters. At the end is a string that is fastened to the ceiling. I want to know what that tension is, and I want to know what that force is. Okay. Now, what I'm going to do is make an observation. It's not moving. It's not doing anything, which is awesome. Because if it's not moving up, down, left, right. So it is in translational equilibrium. Also, it's not rotating about that point or that point or that point or anywhere in between. Therefore, it is in rotational equilibrium. If it's in translational equilibrium, the sum of the forces, and in this case, the one that we care about, y, is equal to 0. In rotational equilibrium, the sum of the torques is equal to 0. And it's about a particular point which I will call A. Now, what point is A? What I typically do is I could either pick this part or that part. And that's because torque is force times the lever arm. The reason why I would pick either here or there is that the torque contribution here from F is 0, because the distance from F to the rotation point is 0. Now, so I would choose either here or here. I'm going to pick here because it's typically the leftmost point that I normally go with. It's just tradition. You could do the other way, it doesn't matter. So 0 equals the sum of the torques. I can ignore this one because it's not, because it's at the point. The two forces are mg and tension. The two lever arms are x1 and x2 plus x1. The distance from that force to A is x1. The distance from there to there is x2 plus x1. Now I only need to worry about the signs. We could do this one of two ways. Clockwise rotations are positive, counterclockwise rotations are negative. Or we could use the right-hand rule. To the right, tension is up, thumb is out, so the one involving the tension is positive. From there to that force is to the right, the force is down, the thumb goes into the page. You're smirking. You don't get it?
No, I get it.
Okay. Then why are you smirking? Oh, yes. Another benefit of being left-handed is because I have a pen in my left hand, and so I use my right hand. So now I solve for T. x1 mg is equal to T x2 plus x1. So x1 mg over x2 plus x1 is equal to T, which is 429.8 divided by 3 and 4. So the tension is 112 newtons. Now, to get F, the best way to do this is to use translational equilibrium because it's not moving up or down. We could use rotational equilibrium about that point, or the faster way is to use translational. The sum of the forces vertically is equal to 0. The forces up are F and T. The force down is mg. I'm looking for F. So mg minus T is equal to F. M is 20, G is 9.8, T is 112, and that gives me 84. So the force at this point, oh, and we might as well since I got 7 minutes. What I'm going to do is I'm going to sum the torques around B. So B is that point. the forces are M, G, and F. The distances are x2 and x1 plus x2. The distance from the rotation point to F is x plus 2. From there to there is x2. So going from there left, using your right hand, down, the mg force produces a positive torque. Left, up, into the page, that makes it negative. And all of these are equal to 0. So F, x1 plus x2, is equal to mg x2, and mg x2 is equal to x1 plus x2, or whatever this is. So m is 20, 9.8, 3 over 4 plus 3, and you should get 112. Oh, okay, it was 804. All right. Yeah, okay, I was looking at that one. All right, thank you. 84 newtons. So it's confirmed. And so that's it. That's a torque bar, and so you could pick any of the points. It doesn't really matter. So that's it. Any other last minute questions? Because I think this is a really good stopping point to get. All right. $20. Thank you already. Venmo or cash accepted. And that's it. Thank you. Bye-bye.